Hello, and thank you for taking the time to listen to this presentation about increasing ecological relevance of chemical risk assessments using geospatial approaches. I will point out there are two posters providing more detail on these case studies, and you can see them listed below. In 2017, the European Center for Ecotoxicology and Toxicology of Chemicals, or SETAC, initiated a task force to investigate current capabilities in making GIS-based, spatially explicit ecological risk assessment. The key aim of this task force was to explore whether georeferenced chemical risk assessments can be tailored to highly resolved local landscape characteristics and ecology to account for spatial heterogeneity. The task force began with a search for applicable and available data. These data were used to make two case studies to investigate techniques and methods for combining disparate data sets and to explore how distributions of spatially referenced chemical exposure and ecological assemblages can be integrated to assess and interpret risk. The task force is composed of a number of individuals and organizations, and I'd like to acknowledge them, as this is a joint work to which each person brings their own perspective and passion. Current prospective chemical risk assessment frameworks do not directly address the landscape scale heterogeneity of exposure and ecological receptors. In order to achieve high levels of protection, generic frameworks assume that reasonably worst-case chemical exposures co-occur spatially and temporally with species assemblages that are most sensitive to the chemical's toxicity. At locations and times in the environment where these metrics co-occur, mitigation and conservation practices might not be deployed where they're most needed, and conventional risk assessment may be overprotective. Our key aim was to assess the utility of georeferenced chemical exposure and ecological data for making prospective ecological risk assessment over large spatial scales, which enable the influence of heterogeneity to be considered. Our focus was to explore the utility of available data and capability of methods to integrate information at varying levels of resolution. To do this, we needed information on chemical emissions as well as the related aquatic receiving environments. And from this, we can generate georeferenced predicted environmental concentrations. We also needed ecotoxicology information for those chemicals as they relate to the biological quality elements, or BQEs, such as fish, algae, aquatic invertebrates, and macrophytes. Finally, georeferenced information about the location, quality, and quantity of those ecological receptors is needed. Using these data, we investigated how distributions of spatially referenced chemical exposure and ecological assemblages can be integrated to assess and interpret risk. For estimation of risk, we used the exposure toxicity ratio, or ETR, which relates a predicted environmental concentration to an acute or chronic ecotox endpoint relevant to that BQE. Finally, we overlaid risk data with the actual ecological status of Water Framework Directive biomonitoring sites to assess if relationships between estimated risk and measured ecological status could be observed. Keep in mind that the key aim was to explore and demonstrate how spatially referenced exposure and ecological receptor data could be integrated for a refined assessment, rather than to explicitly quantify risks. Therefore, the case study should not be interpreted as necessarily consisting of the best estimates of exposure or effects. While the task force started out with the goal of looking at pan-European approaches, we ultimately focused on Germany, and in particular the state of Hesse. The study area was chosen primarily due to the availability of high-quality Water Framework Directive ecological data for aquatic environments, in conjunction with detailed hydrologic data to which the ecology data were spatially located. These data contained almost 4,000 sample locations, reporting observed data from one or more of the 4 BQEs. This is shown on the map on the left. Attributes included location, abundance, evaluation of ecological state, as well as other scoring values. Of particular interest was the ranking of ecological status for each site. This incorporated aspects such as diversity and abundance into a single score, and this was a way to relate a scoring of ecological health consistently across BQEs. This is the right side map. We selected 2 aquatic case studies based on different chemicals, emission pathways, and spatial temporal scales of exposure. Keeping with our plan to develop and evaluate a spatially referenced risk assessment framework, we're presenting the work using general chemical classes and not specific active ingredients, as the focus should be on the approach and not the specific exposure or risk numbers for an individual chemical. The surfactant case study represents an assessment of a widely used anionic surfactant used in domestic cleaning products with environmental emission into the aquatic habitat via constant wastewater treatment plant discharge. The plant protection product case study represents a collection of 3 PPPs, an herbicide, insecticide, and fungicide, applied to winter wheat, winter oilseed rape, and winter barley. These chemicals manage surface water from runoff, erosion, or drift in an episodic manner. Again, the focus is on the methodology of what we're trying to do, not trying to develop the most accurate estimations of emissions or environmental concentrations. Surfactant usage occurs in most households in Europe. Therefore, it is assumed that each wastewater treatment plant receives a mass of surfactant and influent proportional to the population served. The concentration is determined by the per capita water use within these households. Wastewater treatment plant locations were spatially linked to river segments to estimate the mean annual surfactant concentration in receiving waters using the equation shown here. Of particular importance is the ratio of effluent and river flows. This dilution factor is unique to each wastewater location and determines the final river concentration. We actually performed this on the entire set of wastewater treatment plants in Germany, resulting in 2,500 river segment concentrations. But what you see here in Hessen are the 332 wastewater treatment plant river combinations used moving forward. Full references for the datasets used here and elsewhere are available in the supporting information, download accessible on the SETAC website. The PPP case study incorporates several additional aspects compared to the surfactant case study. In this case study, the spatial scale is more highly resolved, as well as the inclusion of temporal dimension. In addition, the PPP case study also includes multiple substances with different modes of action in the form of an insecticide, herbicide, and fungicide, widely used on winter wheat, winter barley, and winter oilseed rape. The Julius Kuhn Institute very kindly modeled a set of daily surface water concentrations for these crops and PPPs using their SYNOPS model. SYNOPS is a Germany-wide field-scale model which utilizes PPP usage survey data to associate applications to individual fields based on regional crop statistics and a stratified random approach. Exposure modeling is performed at a daily time step using regulatory models to simulate drift, drainage, and runoff erosion. Estimated daily 1 and 7-day time-weighted average concentrations in surface water are summarized within the model and stored as the annual 90th percentile of daily concentrations associated with the field for that year. Overall, we included 134,000 applications onto almost 82,000 fields, with over half of the fields receiving applications of 2 or more PPP. To convert the estimated concentrations into a risk metric, we used the exposure toxicity ratio approach. We used publicly reported ecotoxicology data, either the EC50 or the NOAC value, along with our concentrations to determine chronic and acute ETRs for macroinvertebrates, fish, macrophytes, and diatoms. For the surfactant case study, converting the constant single chemical concentration to a river-based ETR was simply a matter of the equations on the previous slide. However, the PPP case study utilized 3 different chemicals along with other spatial considerations. First, we had to sum the ETR values for all 3 PPPs for each of the 81,000 fields. Each field was then linked to the closest stream segment, and if a stream segment had more than one field linked, a summative ETR was calculated. This resulted in about 53,000 fields linked to 18,000 stream segments. The high-resolution hydrology contained a detailed stream network, generally 100-meter segments. To account for hydrologic transport and accumulation, upstream segments, comprising a total of 1,000 meters, were identified for each surface water segment, and the sum of the individual risk indices for all those upstream segments was calculated for each BQE. So in the end, each stream segment had BQE risk values that represented the 1,000-meter upstream situation. With our risk estimations now spatially linked to the rivers, we can then relate each ecological monitoring site with an estimated chemical risk. We wanted to do this so we could examine if any relationship existed between current ecological health and potential chemical exposure. The ecological status metric for each BQE provided the basis for this comparative relationship. The close to 4,000 monitoring locations in Hessian provided varied spatial patterns for ecological health. The two maps on the left show a heat map comparing the ecological status of 2 and 4 for all BQEs, where a status of 2 indicated better ecological health than does the status of 4. You can see the differing spatial patterns. The two maps on the right compare the same ecological status between two BQEs, fish and macroinvertebrates. Again, difference in spatial patterns exist. And this is good because the premise of the task force work was that exposure, and more importantly ecological receptors, are not homogeneous in content, quality, or spatial distribution across the landscape. The focus of our study was to assess the utility of georeferenced data and ecological risk assessment, rather than making highly refined assessments for a chemical. So we're not necessarily aiming to accurately quantify the magnitude of any effects. But here we compared risk values and ecological status for each location. And here are some of the types of comparisons we can make with the predicted risk for different taxonomic groups and different levels of ecological status. There's no apparent relationship between the chronic ETR and ecological status for fish, macroinvertebrates, and macrophytes. One might hypothesize that we would see higher ETR values in streams and rivers with poor ecological status, and this would be shown in the chart by rising values as we move from left to right. We don't see that here, so this suggests that surfactant concentration is not individually driving ecological status. Similar comparisons are made for the PPP case study, in which we've included 3 stressors with 3 different modes of action. But again, there's no apparent relationship between ETR and ecological status. We can see there's much greater variation in risk values compared to the surfactant study. This refined approach allows for examination of multiple stressors that occur in space and time, and these could be applied beyond just pesticides. ETR values suggesting potential risk can be mapped to identify hotspots, and we can use these hotspots and matched ecological status to inform whether remediation for low ecological status or conservation for high ecological status might be required. It's clear there are very few ecological datasets that are sufficiently comprehensive, consistent in content, and that span large enough geographic areas for use in large-scale risk assessment. However, we did demonstrate that it's feasible to make geospatial analyses of the relationships between ecological status and chemical risk at some scales. Our case studies demonstrated that ecological risk assessment and any subsequent remediation or conservation measures can be informed by using spatial approaches where we can identify locations where species assemblages may be at a relatively higher risk. And although beyond the scope of our case studies, the approach here lends itself to assessing aggregated risk from multiple stressors. Framing of landscape scale risk assessment is a critical step, and that requires clear statement of the question to be addressed and must consider how data will be combined, at what resolution, and what methods will be used to integrate data layers. Right now, we're compiling the work of the task force into a publication, an SETAC report. I'd like to encourage you to review the 2 posters on these case studies. These will give you more details on some of the aspects I didn't have time to cover in this presentation, but please leave any questions you might have in the Q&A box on this page. Thank you for your time and attention.